Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable wherever you are. Let your body settle into this quiet space. Where in the world are you watching from? A darkened bedroom where the day has finally released you. A cozy corner where you can finally let your thoughts slow down. Tonight we're going to explore one of the most fascinating questions in all of science and philosophy. What if the universe itself, everything you've ever experienced, might not be quite what it seems? We'll discover the strange behaviour of quantum particles, understand the mathematical patterns that repeat throughout reality, and contemplate what physicists and philosophers have uncovered about the very nature of existence. It's a journey that spans from the smallest possible scales to the entire cosmos, from ancient Greek philosophy to cutting-edge quantum experiments. But don't worry. This isn't going to be an anxiety-inducing dive into existential dread or conspiracy theories. Instead, we'll move slowly and carefully through the actual evidence, the real experiments, the honest uncertainties that scientists grapple with. By the end, I think you'll find not fear, but a kind of peaceful wonder at the beautiful strangeness of it all. We'll discover that even if reality isn't what we thought, that doesn't diminish its meaning or beauty. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours. So settle in. Let your shoulders drop away from your ears. Take a slow breath in and let it out even more slowly. And let's begin our gentle drift through this question that has puzzled thinkers for thousands of years. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the ideas unfold like stars emerging as the sky darkens. We'll take this slowly, together. Let's begin somewhere simple, somewhere we can all recognise. Think about the room you're in right now, the device you're watching this on, the air moving gently through your lungs. It all feels solid, doesn't it? Real, undeniable. The floor beneath you, the walls around you, the warmth of a blanket or the cool touch of evening air. This is reality. We know it because we experience it, every moment of every day. But here's where things start to get interesting. Not in a frightening way, but in a way that opens up wonder. Everything you're experiencing right now, every sensation, every sight and sound is actually being constructed inside your brain. You're not directly experiencing the room around you. You're experiencing your brain's interpretation of electrical signals, its best guess at what's out there based on the information your senses provide. Your brain is building reality for you, moment by moment, a continuous act of creation. Now, this isn't some mystical claim. It's basic neuroscience. Light enters your eyes and triggers chemical reactions in your retinas. Those reactions create electrical signals that travel along your optic nerves. Your brain receives these signals and constructs the experience of seeing. The colours you perceive don't exist out there in the world. They're labels your brain assigns to different wavelengths of electromagnetic radiation. The solid feeling of the floor beneath you is your brain's interpretation of electromagnetic forces between atoms, forces that keep your body from passing through what is, at the atomic level, mostly empty space. Think about that for a moment. The solidity you feel isn't really solidity at all. If you could shrink down to the size of an atom, everything around you would look mostly like empty space with tiny particles held together by invisible forces. The chair you're sitting on, the walls of your room, even your own body, are all made of atoms, and atoms are more than 99.999% empty space. The particles that make up those atoms, the electrons and quarks, are so small compared to the space they orbit in that if an atom were the size of a football stadium, the nucleus would be like a grain of sand at the centre, and the electrons would be specks of dust orbiting somewhere up in the higher seats. And yet, when you touch a wall, it feels solid. When you sit in a chair, it holds you. This isn't an illusion exactly, but it is your brain translating quantum mechanical forces into the experience of solidity, creating the sensation of touch from patterns of electromagnetic repulsion between the electrons in your hand and the electrons in whatever you're touching. Reality, at its foundation, is very different from our everyday experience of it. Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, and they're remarkably good at that. But the universe itself operates on principles that seem strange, even impossible, when we look closely enough. This is where our journey begins, with this recognition that the reality we experience is already, in a very real sense, a construction. It's built by our brains from incomplete information, shaped by the limitations of our senses and the evolutionary pressures that form those senses. We don't see ultraviolet light the way bees do, or hear ultrasonic frequencies the way bats do, or sense magnetic fields the way some birds do. Our version of reality is just that. A version, one possible interpretation of the information available. And this brings us to something that scientists discovered in the early 20th century, something that would shake the very foundations of how we understand existence. Because when physicists began studying matter at its most fundamental level, they found something unexpected, something that suggested reality itself might be far stranger than anyone had imagined. What they discovered was that the universe doesn't seem to exist in a definite state until we look at it, that the very act of observation appears to create the reality we observe. It sounds impossible, like something from a dream or a poorly understood science fiction story. But it's not fiction. It's what the experiments show again and again, with results so consistent and so strange that physicists have spent nearly a century trying to make sense of what it all means. Let's explore what they found gently and carefully, because this is where the question really begins. The story of quantum mechanics begins, as so many scientific revolutions do, with an experiment that refused to make sense. In the early 1900s, physicists were feeling quite confident about their understanding of reality. They had Newton's laws of motion, Maxwell's equations of electromagnetism, a beautiful mathematical description of how the universe worked. Matter was made of particles, light was made of waves, and everything obeyed precise, predictable rules. The universe was like a vast clockwork mechanism, complex but ultimately comprehensible, deterministic and ordered. Then they started looking at individual atoms, individual particles of light, and everything they thought they knew began to unravel. It started with experiments on something called blackbody radiation, the light emitted by hot objects. The equations that worked perfectly for large-scale phenomena kept giving nonsensical answers when applied to atoms. Max Planck, a German physicist, found he could fix the equations by making a strange assumption. He proposed that energy could only be absorbed or emitted in discrete chunks, in little packets he called quanta. It was a mathematical trick, really. Something he thought might just be a useful calculation tool rather than a description of reality. But then other experiments confirmed it. Light, which everyone knew was a wave, sometimes behaved like a particle. Electrons, which everyone knew were particles, sometimes behaved like waves. Albert Einstein won his Nobel Prize not for relativity, but for explaining something called the photoelectric effect, showing that light really does come in particle-like packets called photons. The wave-particle duality wasn't just a mathematical convenience, it was somehow actually true. Light was both wave and particle. Matter was both particle and wave. Depending on how you measured it, you'd get different answers, as if reality itself couldn't make up its mind about what things fundamentally were. This led to a question that sounds almost philosophical. If something can be both a wave and a particle, what is it really, when no one is looking? What is its true nature, independent of observation? And here's where things get genuinely strange, where the universe begins to seem less like a solid, objective thing, and more like something far more elusive. Because the mathematics of quantum mechanics, developed by physicists like Werner Heisenberg, Erwin Schrödinger, and Niels Bohr in the 1920s, suggested something radical. It suggested that particles don't have definite properties until they're measured. They exist in what's called a superposition, a strange state where they're somehow all possible values at once, like a coin spinning in the air, neither heads nor tails until it lands. Schrödinger, trying to show how absurd this seemed, proposed his famous thought experiment with a cat in a box. If quantum mechanics applied to large objects the way it did to small particles, he argued, you could have a cat that was both alive and dead until you opened the box and looked. He meant this as a reduction to absurdity, a way of showing that quantum mechanics must be incomplete. But instead, physicists took it seriously. Maybe, they said, that is how reality works. Maybe things really don't have definite properties until they're observed. Maybe the act of measurement doesn't just reveal reality, but actually creates it. This idea, called the Copenhagen interpretation after the city where Niels Bohr worked, became the dominant way of understanding quantum mechanics, and it's still taught in textbooks today. According to this view, quantum particles exist in a kind of cloud of probability, and only when we measure them do they collapse into a definite state. Before measurement, an electron isn't at position A or position B. It's in both positions somehow, existing as a wave of probability spread across space. When you measure it, the wave function collapses, and the electron appears at one specific location, but which location is fundamentally random, determined only by the probabilities the mathematics describe. Now, you might be thinking, surely this only applies to tiny particles, things too small to see, far removed from our everyday world. And for a long time, physicists thought the same thing. There must be some scale, they reasoned, where quantum weirdness gives way to classical physics, where things become solid and definite and real in the way we experience them. But as experiments became more sophisticated, as scientists learned to manipulate individual particles with extraordinary precision, that boundary kept moving. They've now demonstrated quantum effects in molecules, in tiny diamonds, in objects visible to the naked eye under the right conditions. The quantum world, it seems, isn't as separate from our world as we'd like to think, which raises a genuinely puzzling question about where reality comes from. There's an experiment, first performed in the early 1800s and refined countless times since, that demonstrates the strangeness of quantum mechanics so clearly, so undeniably, that physicist Richard Feynman called it the central mystery of quantum theory, the experiment that contains the only mystery. It's called the double-slit experiment, and once you understand what it shows, reality never quite looks the same again. Let me walk you through it, step by careful step. Imagine you have a barrier with two narrow slits cut into it, and behind that barrier, a screen that can detect particles or light. Now shoot particles, electrons say, one at a time toward the barrier. Each electron will go through one slit or the other, just like if you threw tennis balls at a wall with two openings. You'd expect to see two bright bands on the screen behind the slits, one behind each opening, corresponding to the particles that went through each slit. And if you actually watch the electrons to see which slit they go through, that's exactly what you get. Two bands. Precisely what common sense would predict. But here's where it gets strange. If you don't watch which slit the electron goes through, if you just let them fly through one at a time and hit the screen, you don't get two bands. You get an interference pattern, multiple bands of light and dark, exactly the pattern you'd expect if waves were passing through both slits simultaneously, interfering with each other like ripples on water. Even though you're sending the electrons through one at a time, each individual particle somehow creates an interference pattern, as if it went through both slits at once, as if it interfered with itself. Think about what this means. When you're not watching, each electron seems to take both paths simultaneously, like a wave spreading out and passing through both openings. But when you do watch, when you set up detectors to see which slit the electron actually goes through, it behaves like a particle, going through one slit or the other, and the interference pattern disappears. The very act of observation changes the outcome of the experiment. It's not that we're disturbing the electrons by measuring them. though physicists thought that for a while. Careful experiments have ruled that out. It's that the electrons genuinely seem to exist in a different state when observed versus when unobserved. This has been tested in countless ways, with photons, electrons, atoms, even large molecules made of hundreds of atoms. The result is always the same. Observe them, and they behave like particles. Don't observe them, and they behave like waves taking multiple paths simultaneously. It's as if reality itself is different depending on whether anyone is looking, as if the universe exists in a state of quantum possibility until observation collapses it into definite actuality. Now, what counts as observation is itself a deep question. Does it require a conscious observer? Does a video camera count? Does a stray photon interacting with the particle count? These questions have sparked decades of debate and research. The mathematical formalism of quantum mechanics doesn't mention consciousness at all. It just describes how quantum systems evolve over time and what happens when they interact with measurement devices. But the interpretation, what it all means, that's where things get murky and fascinating. Some physicists, like Eugene Wigner, seriously propose that consciousness might be required to collapse the wave function, that reality remains in a state of quantum superposition until a conscious mind observes it. Others found this idea deeply troubling, too mystical, too far from the objective science they believed in. John Bell proposed that maybe there are hidden variables, information we can't access that determines what will happen, preserving a kind of underlying reality even if we can't see it. But experiments testing Bell's ideas, performed in the 1980s and refined since, have largely ruled out local hidden variables. If there's a hidden reality determining quantum outcomes, it has to operate faster than light, connecting distant particles instantaneously. Which brings us to another quantum strangeness, one that Einstein himself called spooky action at a distance, so disturbing to his sense of how reality should work that he considered it evidence that quantum mechanics must be incomplete. He spent the last decades of his life trying to prove there must be something deeper, some more sensible explanation. But every experiment, every test, keeps confirming the spooky predictions of quantum mechanics, keeps suggesting that reality is genuinely strange in ways that challenge our deepest intuitions about what it means for something to exist. Let's explore what those experiments revealed, because this is where the question of reality's nature becomes truly fascinating. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper that was meant to show quantum mechanics was incomplete. They described a thought experiment, now called the EPR paradox, that demonstrated what they saw as an absurd consequence of quantum theory. If you created two particles together in a certain way, quantum mechanics predicted they would remain connected no matter how far apart they travelled. Measure a property of one particle, say its spin, and you'd instantly know the corresponding property of the other particle, even if it was on the other side of the galaxy. Einstein found this ridiculous. Nothing can travel faster than light. He'd shown that himself with relativity. There must be some hidden information determining both particles' properties from the start, he argued, some reality independent of measurement. But he was wrong in the most interesting possible way. Quantum entanglement, as this phenomenon came to be called, is real. Experiments have confirmed it over and over, with increasing precision and sophistication. When you measure one particle of an entangled pair, you really do instantly affect its partner, no matter the distance separating them. It's not that information is travelling between them faster than light. The mathematics is more subtle than that. But there is a genuine connection, a correlation that can't be explained by anything determined in advance. The particles don't have definite properties until measured, and when you measure one, both somehow acquire definite correlated properties simultaneously. John Bell, in 1964, proved mathematically that no theory based on local hidden variables could reproduce the predictions of quantum mechanics. If quantum mechanics was right, if the correlations it predicted for entangled particles actually occurred, then either information travelled faster than light, or reality itself wasn't local and definite in the way we intuitively believe. Starting in the early 1980s, experiments by Alain Aspect and others tested Bell's inequalities, the mathematical predictions that would differentiate between quantum mechanics and local hidden variable theories. Quantum mechanics won decisively. The correlations are real, stronger than any local hidden variable theory could produce. This means something profound about the nature of reality. Two entangled particles separated by any distance are not two separate things that happen to be correlated. They're part of a single quantum system, a single entity in a very real sense, even though they're spatially separated. Space and separation, the very things that seem most fundamental to our experience of reality, seem to be less fundamental than this quantum connection. At the quantum level, the universe is not made of separate, independent objects. It's woven together in ways that transcend space and time as we understand them. And this gets even stranger when you consider the implications for the universe as a whole. Every particle in your body, every atom that makes you up, was once part of the extremely hot, dense state at the beginning of the universe. In those first moments, everything was in contact, everything was interacting, everything was potentially becoming entangled. Even as the universe expanded, as particles separated and cooled and formed atoms and molecules and stars and planets, and eventually you, those quantum connections might persist. You might be entangled with particles scattered across the cosmos, connected in ways that transcend the enormous distances between you. Some physicists have taken this idea further, suggesting that entanglement might be the fundamental structure of reality, more basic than space itself. In theories called ER equals EPR, named after Einstein-Rosen bridges and the EPR paradox, they propose that quantum entanglement and the geometry of space might be two ways of describing the same underlying reality. Space might emerge from patterns of entanglement between quantum particles, like a fabric woven from threads of connection. If this is true, then space itself, the arena in which everything happens, the stage on which the cosmic drama unfolds, might not be fundamental. It might be an emergent property, something that arises from deeper quantum connections. This is where physics starts to sound like philosophy, or even mysticism, though it remains firmly grounded in mathematics and experiment. The equations describe these connections precisely, predict experimental outcomes accurately, even if the implications seem to challenge everything we thought we knew about reality. Things are connected in ways we don't fully understand. The universe is not a collection of separate objects interacting through space. It's something stranger, more unified, more deeply interconnected. And this interconnectedness, this quantum entanglement that links particles across space and time, is one reason some physicists have started to take seriously an idea that would have seemed like pure science fiction just a few decades ago. The idea that brings us to the heart of our question tonight. And it's an idea we'll explore as we continue our gentle journey through this mystery. Now we come to an idea that might sound like it belongs in a science fiction movie, but which serious philosophers and physicists have contemplated with genuine care and rigour. What if our universe is a simulation, a kind of computer program running on some unimaginably advanced substrate? What if everything we experience, every star and galaxy, every thought and feeling, is information being processed, rendered like a video game, but one so sophisticated we can't detect the difference between it and base reality? It's called the simulation hypothesis, and while it might seem far-fetched, there are surprisingly compelling arguments for taking it seriously. The modern version of this idea was formulated most clearly by philosopher Nick Bostrom in a paper published in 2003. Bostrom didn't claim that we definitely live in a simulation. Instead, he presented what's called a trilemma, three possibilities of which at least one must be true. Either intelligent civilizations almost always go extinct before reaching the technological capability to run realistic simulations of their own history, Or such civilizations reach that capability, but choose not to run such simulations for some reason, or we almost certainly live in a simulation. If civilizations can create realistic simulations and choose to do so, Bostrom argued, then simulated realities would vastly outnumber base reality, making it statistically likely we're in one of the simulations rather than the one original universe. Think about the logic carefully. If a civilization becomes advanced enough to simulate conscious beings in a realistic universe, they might run many such simulations, perhaps thousands or millions, simulating their own history to study it, or creating entertainment, or conducting experiments. Each simulation could itself contain civilizations that eventually develop their own simulation technology, creating simulations within simulations. Quickly, the number of simulated realities would dwarf the number of base realities. 1. If you found yourself as a conscious being in this multiverse of simulations, simple probability would suggest you're more likely to be in one of the vastly more numerous simulated realities than in the single base reality. Now, Bostrom's argument doesn't depend on any particular technology. It doesn't require that our universe actually be running on something we'd recognize as a computer. But it's worth considering how rapidly our own computing capabilities have grown. The first electronic computers, built in the 1940s, could perform thousands of calculations per second and filled entire rooms. Today, the phone in your pocket can perform billions of calculations per second. Modern supercomputers can perform quintillions of calculations per second, numbers so large they're hard to comprehend, and this progress shows no sign of stopping. Quantum computers, still in their infancy, promise to solve certain problems exponentially faster than classical computers, exploring vast computational spaces that would be impossible to search otherwise. If this trend continues, if civilizations don't destroy themselves first, it's not hard to imagine technology 1,000 years from now, or 10,000, or 1,000,000, reaching capabilities that seem like magic to us. The ability to simulate individual atoms, individual quantum particles, an entire universe evolving according to physical laws, might be achievable with sufficient computing power and understanding, and if it's achievable, and if civilizations survive long enough to achieve it, then Bostrom's argument kicks in. Most conscious beings would be simulated, not base reality, making it probable that you, reading this now, are among the simulated. This might feel unsettling, or it might feel absurd, but there's a deeper philosophical tradition behind it. The idea that reality might be something other than it appears, that we might be perceiving shadows rather than substance, goes back at least to Plato's allegory of the cave, written in ancient Greece around 2,400 years ago. Plato imagined prisoners chained in a cave seeing only shadows on a wall, taking those shadows for reality itself, never knowing about the fire and the objects casting the shadows, let alone the world beyond the cave. What if, Plato asked, our entire experience is like that, a limited perception of a deeper reality we can't directly access? René Descartes, in the 1600s, famously questioned whether he could know anything with certainty, whether everything he perceived might be an illusion created by a malicious demon. He concluded he could be certain only of his own thinking, his own existence as a thinking thing. Quote zero became the foundation he built his philosophy on. The one thing he couldn't doubt. Eastern philosophies have long held that the world we perceive is illusion, Maya in Hindu tradition, a veil obscuring deeper truth. The simulation hypothesis, in a sense, is these ancient ideas dressed in modern technological language, the perennial philosophical question of what is real translated into terms of information and computation, and this translation might actually give us new ways to investigate the question. There's something peculiar about our universe that physicists have noticed, something that might be a clue about its fundamental nature. The universe is mathematical, not just in the sense that we can describe it with mathematics, but in a deeper sense. The laws of physics are mathematical relationships. Equations that hold with perfect precision across billions of light years and billions of years of time. An electron here behaves exactly like an electron in a galaxy so distant its light has been travelling to us since before Earth formed. The charge of an electron, the mass of a proton, the speed of light, these fundamental constants don't vary. They're the same everywhere, always as far as we can tell. This is not obvious. The universe could have been chaos, different rules in different places, physical laws that changed over time, but it's not. It's ordered, law-governed, mathematical. Albert Einstein once remarked that the most incomprehensible thing about the universe is that it's comprehensible, that we can understand it through mathematics at all. Eugene Wigner, a physicist who thought deeply about these questions, wrote a famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He pointed out that mathematics, developed by humans for human purposes, turns out to describe physical reality with astonishing accuracy. Equations discovered by thinking abstractly about numbers and shapes turn out to govern how particles behave, how stars shine, how galaxies spiral. Why should this be? One possibility is that mathematics is the language of reality because reality is, at its core, mathematical. Not made of matter or energy primarily, but made of relationships, patterns, information that can be described mathematically. This idea has been developed most thoroughly by physicist Max Tegmark in what he calls the mathematical universe hypothesis. Tegmark proposes that our universe is not just described by mathematics. It is mathematics, a mathematical structure that has the property of being self-aware, or at least containing subsystems that are self-aware. In this view, physical existence and mathematical existence are the same thing. If reality is fundamentally mathematical, if matter and energy and space and time are all just patterns in some abstract mathematical structure, then the simulation hypothesis becomes less strange. A simulation is, after all, a mathematical structure being computed. The difference between a simulated universe and a mathematical universe might be smaller than we think, or might not exist at all. Both are patterns of information organised according to mathematical rules. Whether those patterns are instantiated in what we call physical matter, or in some computational substrate might not matter, might not even be a meaningful distinction. Consider how physics has progressed over the last century. We've discovered that matter is made of atoms. Atoms are made of particles. Particles are made of quarks and leptons. And quarks and leptons might be vibrations of one-dimensional strings in higher dimensional space, according to string theory. At each level, we found not stuff but patterns, relationships, mathematical structures. An electron isn't a tiny ball of something. It's a particular solution to the Dirac equation, a mathematical description of how quantum fields behave. The deeper we look, the more reality seems to be made of mathematics rather than matter. And there's another suggestive feature of our universe. The laws of physics are remarkably simple when expressed in their fundamental form. The standard model of particle physics, which describes all known particles and 3 of the 4 fundamental forces, fits on a t-shirt. General relativity, Einstein's theory of gravity and space-time, can be written in a single elegant equation. These laws are complex in their consequences. They produce the rich diversity of structures we see around us, stars and planets and life and consciousness. But the underlying rules are relatively simple, exactly what you'd expect if you were designing a universe to simulate. Simple rules that can be computed efficiently, but which give rise to complex emergent behaviour. This is actually a principle in computer science and mathematics called computational irreducibility. Simple rules, iterated over and over, can produce behaviour so complex that the only way to know what will happen is to actually run the computation. You can't predict the result by any shortcut. The universe's evolution from the Big Bang to now might be an example of this. Simple physical laws, applied consistently over 14 billion years to an expanding universe full of particles and fields, producing the cosmos we see and the complexity we're part of. It's a beautiful idea, reality as mathematics, but it raises as many questions as it answers. If the universe is a mathematical structure, why this particular structure and not another? There are infinitely many possible mathematical structures. What determines which ones exist as universes? We'll explore these questions as we continue, but for now, let this thought settle gently into your mind and carry us forward into deeper waters. In the early 20th century, Max Planck discovered something fundamental about the universe while studying the light emitted by hot objects. Energy, he found, comes in discrete units, in packets he called quanta. You can have one quantum of energy or two or three, but you can't have 1.5 quanta. Energy is quantized, digital rather than analog, and this discovery was the birth of quantum mechanics. But Planck discovered something else, something even more profound. By combining fundamental constants of nature in certain ways, he found natural units of measurement. Scales at which quantum mechanics and gravity and relativity all become equally important. These scales are astonishingly small. The Planck length is about 10 to the negative 35 meters, so small that if you expanded a single atom to the size of the observable universe, the Planck length would still be smaller than an atom. At this scale, space itself might become discrete, quantized like energy, made of indivisible pixels like an image on a screen. Below the Planck length, our current theories of physics break down. We don't know how to describe space-time at these scales. General relativity and quantum mechanics, our two great theories of the very large and very small, give contradictory answers when applied to regions smaller than the Planck length. This has led some physicists to propose that space itself might be fundamentally discrete, that there might be a smallest possible distance, pixels of space that can't be subdivided further. Space would be digital, not continuous, like a grid of points rather than a smooth surface. Similarly, there's a Planck time, about 10 to the negative 44 seconds, potentially the smallest meaningful unit of time, the frame rate of the universe if time is indeed quantized. And there's a Planck energy, an upper limit to how concentrated energy can become before the fabric of space-time itself becomes unstable and forms black holes. These aren't just theoretical constructs. They emerge naturally from the mathematics when you try to combine quantum mechanics with general relativity, and they're deeply suggestive if you're thinking about simulation. A simulated universe wouldn't be infinitely detailed. It would have a resolution, a smallest pixel size below which details don't exist because they're not being computed. It would have a frame rate, a shortest time step between updates, and it would have limits on how much information could be packed into a given volume, limits on computation density. Our universe appears to have exactly these properties. If the Planck scale represents fundamental limits rather than just the limits of our current theories, you could argue this is simply what physics looks like at extreme scales, that quantum gravity naturally leads to discrete structure. But you could equally argue it's exactly what you'd expect if reality were being computed, if the universe were running on some substrate with finite resources, unable to simulate infinite precision or infinite density of information. There's another piece of evidence along these lines, something called the holographic principle. It comes from studying black holes, those regions of space-time where gravity is so strong that nothing, not even light, can escape. Stephen Hawking showed in the 1970s that black holes have entropy, a measure of disorder or information content. But bizarrely, the entropy of a black hole is proportional not to its volume, as you'd expect for a three-dimensional object, but to its surface area. It's as if all the information about what's inside the black hole is somehow encoded on its two-dimensional surface. This led physicists like Gerard 't Hooft and Leonard Susskind to propose the holographic principle, the idea that our three-dimensional universe might be a kind of projection from information encoded on a two-dimensional boundary. Like a hologram where a flat surface encodes a three-dimensional image. If this is true, then the universe has fewer degrees of freedom, less information content than you'd expect for a genuinely three-dimensional space. Again, exactly what you might expect in a simulation trying to minimize computational load. Why compute the full three-dimensional interior when you can get the same results by computing only a two-dimensional surface and projecting from there? The holographic principle has become central to modern theoretical physics, particularly in something called the ADS/CFT correspondence, a mathematical equivalence between gravitational theories in one space and quantum field theories in a space with one fewer dimension. This correspondence has been checked in countless ways and always holds, suggesting something deep about the structure of reality, that dimension itself might be less fundamental than we thought. That the three-dimensional space we experience might emerge from something deeper and simpler. All of these pieces, the quantization of energy and possibly space and time, the fundamental limits at the Planck scale, the holographic principle suggesting reality is lower dimensional than it appears, they're not proof of simulation, but they're consistent with it. They show that our universe has features you'd expect if it were being computed, if it emerged from information processing rather than being made of continuous, infinitely divisible stuff existing in a container of smooth, continuous space and time, and that's worth pondering carefully. There are numbers that define our universe, fundamental constants that determine how physics works, the strength of gravity, the charge of an electron, the mass of a proton, the speed of light, and about 20 others. These constants appear in the equations of physics, and their values determine what's possible in our universe. Stars shine because these numbers have the values they do. Atoms are stable, chemistry works, life emerges, all because these constants fall within very narrow ranges. Change any of them by even a small amount, and the universe becomes unrecognizable, sterile, unable to support complexity or life. This is called the fine-tuning problem, and it's been recognized since at least the middle of the 20th century. Take the strength of the strong nuclear force, the force that holds atomic nuclei together. If it were just a few percent weaker, only hydrogen would be stable. No atoms heavier than hydrogen could form. No carbon, no oxygen, no chemistry, no life. If it were a few percent stronger, hydrogen would be rare because protons would quickly bind into helium and heavier elements in the early universe. Stars would burn differently, possibly not forming at all. The window for a universe with long-lived stars and complex chemistry is remarkably narrow. Or consider the cosmological constant, the energy density of empty space itself, which drives the accelerating expansion of the universe. It's astoundingly small, but not zero. If it were much larger, even by a tiny fraction, the universe would have expanded so rapidly that matter could never clump together to form galaxies and stars. If it were negative by too much, the universe would have collapsed back on itself before stars could form. The value we observe is fine-tuned to about 1 part in 10 to the 120th power, a precision so extreme it's almost impossible to comprehend. It's like balancing a pencil on its point for billions of years, but billions of times more precisely than that. Why do these constants have the values they do? Why is the universe so precisely calibrated for complexity? One answer is the anthropic principle, the observation that of course we find ourselves in a universe that permits life, because if it didn't, we wouldn't be here to observe it. If there are many universes, perhaps infinitely many, with different values of these constants, then it's not surprising that we're in one of the rare ones that allows observers to exist. We couldn't be anywhere else. This leads to the idea of a multiverse, vast numbers of universes with different physical laws, different constants, most of them empty and sterile, but a few, like ours, capable of producing stars and planets, and life and consciousness. The multiverse is a serious idea in modern cosmology, arising from theories of inflation and from the mathematics of string theory, which predicts an enormous landscape of possible universes. If the multiverse exists, fine-tuning isn't mysterious, it's selection bias. We observe a fine-tuned universe because those are the only ones capable of being observed. But there's another possible explanation, and it ties directly to our question about simulation. If our universe is designed, whether by a creator deity or by some civilization running a simulation, then fine-tuning is exactly what you'd expect. You'd choose the constants carefully to create a universe with interesting properties, with complex structures, perhaps with life and consciousness. A simulation designed to study evolution or intelligence or the development of civilizations would naturally be fine-tuned for those purposes, with laws and constants chosen to make those phenomena possible. This doesn't prove simulation, of course. The anthropic explanation and the multiverse are equally consistent with the fine-tuning we observe, but it does make simulation less implausible. If you're a civilization wanting to simulate a universe, you'd choose the parameters carefully, and you'd probably choose them to allow for life and intelligence, because those are interesting. You probably wouldn't simulate 14 billion years of sterile hydrogen expanding into cold darkness. You'd simulate conditions that lead to galaxies and stars and planets, and eventually observers who might themselves wonder about the nature of reality. There's something else to consider about these fundamental constants. They appear to be arbitrary. Our theories don't explain why they have the values they do. We measure them and we plug them into our equations, but we don't derive them from deeper principles. This is often seen as a limitation of current physics, something we hope to overcome with a more complete theory. But it's also consistent with these being parameters set from outside, configuration options for the simulation chosen to produce particular outcomes. In computer programming, you might set parameters at the beginning of a simulation. Gravity strength equals this, electromagnetic force equals that, and then let the simulation run according to those settings. The fundamental constants of our universe might be exactly that. Parameters set when the simulation was initialized, chosen carefully to produce a universe worth simulating. It's speculation, but it's speculation grounded in genuine features of how our universe appears to be structured, and it's worth holding that possibility gently in mind as we explore further into this mystery. We return now to quantum mechanics, to that strange feature where observation seems to affect reality, where particles exist in superposition until measured and then collapse into definite states. This is more than just an interesting quirk of physics. It might be a clue about the fundamental nature of reality, about whether anything exists when no one is looking, and it raises profound questions about the role of consciousness in creating or determining the world we experience. Questions that connect to simulation in unexpected ways. Remember the double-slit experiment. Send electrons through one at a time without observing which slit they pass through, and you get an interference pattern, as if each electron goes through both slits simultaneously. But observe which slit they go through, and the interference pattern disappears. The electrons behave differently depending on whether they're being observed. This has been verified countless times with countless variations. The phenomenon is real, even if its interpretation remains debated among physicists and philosophers. But what counts as observation? Early quantum physicists, including some of the theory's founders, wondered whether consciousness might be necessary to collapse the wave function, to turn quantum possibilities into classical actualities. John von Neumann, one of the 20th century's great mathematicians, analysed the measurement process mathematically and concluded that the chain of measurement, the particle affecting the detector, affecting the measuring device, affecting the scientist's brain, had to terminate somewhere in consciousness. Otherwise, everything would remain in quantum superposition, an infinite regress of unmeasured measurements. This led to interpretations of quantum mechanics that gave consciousness a central role. Eugene Wigner seriously proposed that consciousness causes wave function collapse. According to this view, reality exists in a state of quantum possibility until a conscious mind observes it, at which point it becomes actual and definite. Before conscious observers existed in the universe, everything might have existed in superposition, in a kind of potential state, and consciousness, when it emerged, began collapsing possibilities into actualities, creating the definite classical world we experience. Most physicists today reject this interpretation as too mystical. Too far from the objective materialism that science is built on. They prefer interpretations that don't require consciousness to play any special role. The many-worlds interpretation, for instance, says that all possible outcomes of quantum events actually occur, but in separate branches of reality that can't interact. When you measure an electron's position, the universe splits into versions where it's at position A and versions where it's at position B, and you, the observer, split too, with one version of you seeing A and another seeing B. No collapse, no special role for consciousness, just universal wave function evolution and branching. Or there's decoherence, the idea that quantum superpositions are fragile and quickly destroyed by interactions with the environment. A particle might be in superposition when isolated, but as soon as it interacts with the environment, with stray photons and air molecules and thermal vibrations, the superposition decoheres into a definite classical state. No consciousness required, just interaction with a complex environment. Many physicists find this interpretation attractive because it explains the classical quantum boundary without invoking anything mysterious. But here's where simulation becomes relevant. In a simulated universe, you wouldn't render everything in full detail all the time. That would be computationally wasteful. You'd render only what's being observed, what needs to be computed to maintain the consistency of the simulation. Video games do this constantly. The world exists in full detail only where the player is looking. Turn your back and the level of detail decreases or the computation stops entirely. Turn back around and it renders again, seamlessly, creating the illusion of a persistent world. If our universe is a simulation, the observer effect in quantum mechanics makes perfect sense. Things exist in a low information state, a superposition of possibilities, until observation requires that the simulation compute them in detail. The act of measurement is the signal that this part of reality now needs to be rendered at full resolution, collapsed from possibility into actuality. It's not that consciousness is magic. It's that observation requires computation, and the simulation is optimizing resources by computing only what's necessary. This would explain why particles behave like waves when unobserved. The simulation isn't tracking their exact position, just the probability wave that describes where they might be. When observation occurs, when the wave needs to collapse to a specific position because something is checking, the simulation makes a quantum choice, weighted by the probabilities, and suddenly there's a definite particle at a definite location. It's rendering on demand, computing reality as needed rather than wastefully simulating every particle's exact position and momentum at all times. This interpretation is speculative, not mainstream physics, but it's not inconsistent with what we observe. It makes the observer effect less mysterious by providing a mechanism, computational optimization, that explains why observation matters. Whether this is how it actually works, we can't say. But it's a possibility worth considering, a way of understanding quantum mechanics that might make more sense if reality is information being processed rather than matter existing in space. And that possibility shifts how we think about consciousness and observation, and what it means for something to be real. If we live in a simulation, you might expect to find glitches, errors in the code, moments when reality doesn't quite work as it should. People have certainly reported such experiences throughout history. The Mandela effect, where large groups of people remember events differently from how they actually occurred, believing Nelson Mandela died in prison in the 1980s when he actually lived until 2013. Or remembering the Berenstain Bears as the Berenstein Bears, a children's book series whose title many people confidently misremember. Strange coincidences, déjà vu. Moments when the world seems to repeat or stutter, all sometimes offered as evidence of simulation glitches. But we should be careful here. Human memory is notoriously unreliable. We don't record experiences like a video camera. We reconstruct memories each time we recall them, and those reconstructions are subject to errors, biases, suggestions from others. The Mandela effect is easily explained by false memories spreading through social networks, people reinforcing each other's errors until they feel certain about events that never happened. Coincidences happen more often than we expect because we're pattern-seeking beings who notice the hits and forget the misses. Déjà vu is likely a quirk of how the brain processes information, a temporary confusion in memory systems creating the false sensation of having experienced something before. So these subjective experiences probably aren't evidence of simulation glitches, but there are more interesting anomalies in physics itself, genuine mysteries that current theories can't fully explain, though whether they're glitches or just gaps in our understanding is impossible to say. Consider the measurement problem in quantum mechanics we've been discussing. The fact that observation affects outcomes, that reality seems to exist differently when measured versus unmeasured, is an anomaly. It's not how we'd expect reality to work if it were objective and independent of observers. It's more like how we'd expect a simulation to work, rendering details only when needed. Or consider dark matter and dark energy, which together make up about 95% of the universe's mass energy content. Dark matter is matter that doesn't interact with light, invisible to our telescopes, detected only through its gravitational effects on visible matter. Dark energy is even stranger, a kind of anti-gravity force causing the universe's expansion to accelerate. We've given these phenomena names, but we don't know what they are. We've never directly detected dark matter particles despite decades of searching. Dark energy might be the energy of empty space itself, but calculations of how much energy empty space should have give answers that are wrong by more than 100 orders of magnitude, possibly the worst prediction in the history of physics. These could be failures of our theories, phenomena that we'll understand once we develop better physics. But they could also be something else, features of the simulation that weren't meant to be noticed, computational placeholders, or shortcuts that only became apparent when we looked carefully enough. If you're simulating a universe, you might use simplified models for things that don't directly affect the phenomena you care about. Dark matter could be a computational hack, a way to produce the gravitational effects needed for galaxy formation without simulating actual particles. Dark energy could be a fidge factor, keeping the expansion rate where you want it. There are also curious numerical coincidences in physics. Why is the universe about 13.8 billion years old, and why did stars form when they did, and why is the universe's expansion accelerating at exactly this epoch? These seem like unlikely coincidences unless they're not coincidences at all, unless the simulation is designed to reach interesting features right around now, when observers have evolved to wonder about them. Again, this is speculation, not science, but it's a way of thinking about anomalies that makes them less random and more meaningful. Then there's the horizon problem, the puzzle of why the universe looks the same in all directions even though different regions of the sky are too far apart to have ever communicated with each other. Inflation, a period of exponential expansion in the universe's first fraction of a second, is the standard explanation. It works mathematically, but it requires incredibly precise fine-tuning of the inflaton field's properties. Or you could think of it as initial conditions set at the start of the simulation. The universe initialized in a low-entropy, smooth state, because that's what produces interesting results. None of these anomalies prove simulation. Each has possible explanations within standard physics, though some of those explanations require accepting fine-tuning or multiverses, or other concepts that strain intuition in their own ways. But taken together, these features of our universe, the quantization, the observer effects, the fine-tuning, the mysteries we can't explain, they paint a picture that's at least consistent with simulation. Reality has some of the properties you'd expect if it were being computed, if it emerged from information processing constrained by computational limits. And that's a genuinely interesting pattern worth considering carefully as we move deeper into these questions. Let's think about information for a moment. About what it means and why it might be more fundamental than matter or energy. Information is a strange thing. It's not made of anything physical, yet it can be stored in many different physical forms. The same piece of information, say the text of a poem, can exist as ink on paper, as magnetic domains on a hard drive, as electrical pulses in a computer's memory, as light travelling through fibre optic cables, as sound waves when spoken aloud. The information remains the same even though the physical substrate changes completely, which suggests that information is somehow separate from, maybe even more fundamental than, the physical stuff that carries it. Physicist John Archibald Wheeler proposed what he called it from bit, the idea that information is the most basic constituent of reality. Every it, every particle, every field, every feature of the universe derives its existence from information, from bits of binary data, yes or no answers to questions about the universe's state. In Wheeler's view, asking nature questions and receiving answers, making observations and getting information is what brings reality into being. Without the questions, without the information generated by observation, there might be no definite reality at all, just unrealized potential. This connects to quantum mechanics in a deep way. Quantum states can be described as information, and quantum processes can be understood as information processing. When a photon travels from a star to your eye, it's not just a physical particle moving through space. It's carrying information about the star's temperature, its chemical composition, encoded in the photon's wavelength and polarization. When the photon hits your retina, information transfer occurs. Your eye decodes the information, your brain processes it, and you gain knowledge about a star that might be hundreds of light years away. The photon was a carrier of information, and its absorption was an information processing event. Quantum entanglement, too, can be understood in terms of information. Entangled particles share information in a way that transcends space. Measure one, and you instantly gain information about the other, no matter how far apart they are. The correlation is informational, a connection in the pattern of data rather than a physical connection through space. Some physicists have proposed that space itself might emerge from patterns of quantum information, that the three-dimensional arena we move through is not fundamental, but is generated by the way quantum bits of information are connected and organized. This view of reality as fundamentally informational rather than material fits naturally with the simulation hypothesis. A simulation is, after all, information processing, patterns of bits being manipulated according to rules. If reality is information, then the distinction between a simulated universe and a physical universe becomes unclear, possibly meaningless. Both are patterns of information organized and processed according to mathematical laws. One might run on what we call a computer, but what is a computer except a physical system designed to process information? And what is the universe except a physical system that processes information through quantum interactions and the evolution of fields and particles? There's a concept in computer science called the Church-Turing thesis, which states roughly that anything that can be computed by any physical process can be computed by a universal Turing machine, a simple theoretical computer proposed by Alan Turing in the 1930s. If this is true, and most computer scientists believe it is, then any physical process, any evolution of any physical system, can be simulated by a computer given enough time and memory. The universe's evolution from the Big Bang to now could, in principle, be computed. Not by any computer we could build with current technology, but by some sufficiently advanced computational system it could be done. And if it could be done, if the universe's evolution can be fully computed from initial conditions and physical laws, then what's the difference between the computation and the actual universe? What makes one real, and the other merely simulated? If you had a perfect simulation of a conscious being, processing information in exactly the same way a brain does, following the same rules, generating the same patterns of neural activity, would that simulated consciousness be any less real than a biological one? Would it have different experiences, different qualia, different inner life? Or would it be conscious in exactly the same way, its substrate being irrelevant to its subjective experience? These questions don't have clear answers. Philosophers and scientists have debated them for years without reaching consensus. But they point to something important about the simulation hypothesis. If reality is information, If consciousness is information processing, if the universe itself is a kind of cosmic computation, then being simulated doesn't make us less real. It just describes what kind of existence we have. Information patterns rather than irreducible physical substance, processes rather than things, relationships rather than objects. And that description might be more accurate regardless of whether we're in a simulation, because modern physics increasingly suggests that's what reality is at its deepest level, information all the way down. Consciousness is perhaps the deepest mystery in all of science. We know it exists because we experience it directly. You're conscious right now, aware of these words, aware of your surroundings, aware of yourself as a thinking being. But how does consciousness arise from matter? How do physical processes in the brain, neurons firing and chemicals flowing, create the subjective experience of what it's like to be you? This is called the hard problem of consciousness, distinguished from the easy problems like explaining how the brain processes information or controls behavior. The easy problems are just complex neuroscience. The hard problem is something else entirely. Think about color. When you see something red, your brain is processing light with a wavelength of about 700 nanometers. But the experience of redness, the quale as philosophers call it, the subjective what it's like to see red, doesn't seem to be explained by wavelengths or neural firing patterns. Someone who had never seen colours, who knew everything about light and eyes and visual cortex but had been blind from birth, wouldn't know what red looks like. They'd have all the objective knowledge but lack the subjective experience. This suggests there's something about consciousness that isn't captured by purely physical descriptions, or at least it seems that way. Some philosophers, called dualists, argue that consciousness must be something separate from physical matter, a non-physical mind interacting with the physical brain. But dualism faces serious problems. How does a non-physical mind interact with physical neurons? What's the mechanism? Where does it happen? Neuroscience has shown that every mental process we can study correlates with brain activity. Damage specific parts of the brain, and specific aspects of consciousness change or disappear. There's no evidence of anything beyond the physical brain being needed to explain behavior and cognition. Other philosophers, materialists, argue that consciousness must be physical, that it emerges from the complexity of neural information processing in ways we don't yet fully understand. Just as wetness emerges from collections of water molecules, even though individual molecules aren't wet, maybe consciousness emerges from sufficiently complex information processing, even though individual neurons aren't conscious. This view is hopeful that neuroscience will eventually explain consciousness, that the hard problem will turn out to be just another easy problem once we understand enough about the brain. But here's where simulation becomes relevant in an interesting way. If consciousness is information processing, if subjective experience emerges from particular patterns of information being organized and transformed in particular ways, then consciousness doesn't depend on being implemented in biological neurons. It could be implemented in silicon, in quantum computers, in whatever substrate the simulation runs on. A simulated person, if the simulation is detailed enough, would be conscious in exactly the same way a biological person is. They'd have real experiences, real awareness, real inner life. Being simulated wouldn't make their consciousness an illusion. It would just mean their consciousness is implemented differently than ours, running on different hardware but executing the same patterns of information processing. This has profound implications. If we're in a simulation, that doesn't mean we're not conscious. It doesn't mean our experiences aren't real. You're thinking right now. You're aware. That's undeniable. The one thing Descartes was certain of. The substrate doesn't matter. What matters is the pattern, the organization of information, the process of thinking and experiencing. Whether that process runs on neurons or on some computational substrate we can't even imagine, doesn't change the fact that it's happening, that there's something it's like to be you. Some philosophers even argue that consciousness might be fundamental, not emergent from information processing, but rather a basic feature of reality like charge or mass. This view, called panpsychism, suggests that all information processing systems have some degree of consciousness. Perhaps very simple for simple systems and complex for complex ones like brains. If this is true, then consciousness would be present throughout the universe, woven into the fabric of reality itself, and the simulation, if that's what we're in, would be conscious in some sense, aware of itself through all the conscious beings it contains. This might sound strange, but it's not more mysterious than materialism's claim that consciousness emerges from unconscious matter when organized in the right way. Both views struggle to explain the hard problem. Both require accepting something that seems almost magical, either that complex information processing creates inner experience from nothing, or that inner experience is built into reality from the start. The simulation hypothesis doesn't resolve this mystery, but it reframes it. If reality is information, and consciousness is information processing, then maybe they're two aspects of the same thing. Your consciousness right now, reading this, thinking these thoughts, that's real regardless of what underlying reality might be. The experience is undeniable. Whether it's happening in neurons in a biological brain in a physical universe, or in some unimaginable substrate in a simulated universe, doesn't change the fact that it's happening, that you are here, aware, experiencing, existing as a conscious being. And that existence, that awareness, is the most certain thing any of us can know. Everything else we might doubt, but not that we're conscious, not that we're having experiences. That remains true in any reality, simulated or otherwise. And perhaps that's what matters most, not the substrate, but the experience itself. The idea that reality might be illusion or simulation isn't new. Long before computers, long before quantum mechanics, ancient philosophers and mystics contemplated the possibility that the world we perceive isn't the deepest truth. In many ways, the simulation hypothesis is the latest version of questions humans have been asking for thousands of years. Questions about appearance and reality, perception and truth, the relationship between consciousness and the world. Let's explore some of these ancient ideas and see how they connect to what modern physics has discovered. In Hinduism, there's the concept of Maya, usually translated as illusion. According to this doctrine, the material world we experience is not ultimately real. It's a veil, a layer of appearance that obscures deeper spiritual reality called Brahman. Individual consciousness, Atman, is not separate from this cosmic consciousness, but is rather a temporary manifestation of it, like a wave on an ocean believing itself separate from the water. The goal of spiritual practice in this tradition is to see through Maya, to realize the illusory nature of the material world and recognize one's true nature as one with Brahman, eternal and unchanging. This sounds remarkably like the simulation hypothesis. If our universe is simulated, then the physical world we perceive, matter and energy and space-time, is indeed a kind of illusion, patterns of information masquerading as objective reality. The deeper truth would be the computational substrate running the simulation, the base reality outside the simulation, analogous to Brahman underlying Maya. And consciousness, the observer experiencing the simulation, might be the one thing that is genuinely real, the awareness that persists regardless of what reality it finds itself in. Buddhism takes a slightly different approach, but arrives at similar conclusions. The Buddha taught that suffering arises from attachment to impermanent things, from clinging to a self that doesn't actually exist as we imagine it. On close examination, Buddhist philosophers argued there's no unchanging self, no permanent soul. What we call the self is a process, a continuous flow of experiences and thoughts and sensations, like a river that seems to be one thing, but is actually new water flowing moment by moment. The world too is impermanent, constantly changing, and our suffering comes from not accepting this, from trying to hold on to what cannot be held. This resonates with quantum mechanics and the observer effect. Reality isn't fixed and permanent, it's probabilistic, fluctuating, existing in different states until observation collapses possibility into actuality. The self, too, might be more process than thing, patterns of information in the brain constantly changing, consciousness arising moment by moment from neural activity rather than being a permanent unchanging observer. Both Buddhism and quantum mechanics suggest that permanence is illusion, that reality is more fluid and less solid than our everyday experience suggests. Plato's allegory of the cave, written around 2,400 years ago, imagines prisoners who have lived their entire lives chained in a cave facing a wall. Behind them burns a fire, and between the fire and the prisoners, people carry objects that cast shadows on the wall. The prisoners see only the shadows, never the objects or the fire or the world beyond the cave. They take the shadows for reality because they've never known anything else. Plato used this as a metaphor for our condition. We see only appearances, shadows of true reality, which exists in a realm of perfect forms beyond our direct perception. The simulation hypothesis is structurally identical to Plato's cave. We're like the prisoners, experiencing a simulated reality, shadows and echoes of the deeper computational reality running the simulation. We take our experiences for ultimate truth because we can't see beyond them to the substrate they run on. And just as Plato imagined a philosopher escaping the cave and seeing true reality for the first time, we might imagine discovering that we're simulated and somehow accessing knowledge of base reality, though how this would actually be possible remains deeply unclear. René Descartes, in the 1600s, imagined an evil demon powerful enough to deceive him about everything, making him believe in a physical world that doesn't exist. The only thing the demon couldn't deceive him about was his own existence as a thinking being, leading to his famous conclusion, "I think, therefore I am." Everything else could be illusion, Descartes realised, but the fact that he was thinking, that there was an I experiencing thoughts, that couldn't be doubted. This is remarkably similar to our situation if we're in a simulation. Everything we perceive could be simulated, but our consciousness, our awareness of being conscious, that remains real. What's fascinating is that these ancient insights, developed through introspection and philosophical reasoning long before modern science, have been largely confirmed by physics. Reality is less solid, less permanent, less objective than common sense suggests. Consciousness plays a role in determining what we experience. The material world might not be the deepest truth. Ancient wisdom and modern science, approaching from completely different directions, seem to be converging on similar conclusions about the nature of existence, and that convergence is worth contemplating as we continue exploring what it means to be real. The concept of the multiverse, the idea that our universe might be just one among many, perhaps infinitely many, has emerged from several independent lines of reasoning in modern physics and cosmology. It's not science fiction or speculation. It's a serious consequence of theories that otherwise work remarkably well in explaining observations, and interestingly, the multiverse concept connects to the simulation hypothesis in ways that make both ideas either more plausible or more strange, depending on how you look at it. The first source of multiverse ideas comes from cosmic inflation. The theory that the universe underwent a period of exponential expansion in its first fraction of a second. Inflation explains several features of our universe, why it's so flat and uniform, why opposite sides of the sky look the same despite being too far apart to have ever communicated. But the mathematics of inflation, when worked out carefully, suggest that inflation doesn't happen just once. It's eternal, creating bubble universes constantly, each one a separate cosmos with potentially different physical laws and constants. Our universe would be one bubble in an infinite foam of universes, most of them very different from ours. The second source comes from quantum mechanics, specifically the many worlds interpretation. Remember that quantum systems exist in superposition until measured, then collapse to definite states. But what if they don't collapse? What if all possible outcomes actually occur, but in separate non-interacting branches of reality. When you measure an electron and find it at position A, there's another branch where you measure it at position B, another at position C, and so on for all possible positions. The universe is constantly branching into versions that contain all possible outcomes of all quantum events, creating a vast, perhaps infinite, multiverse of parallel realities. The third source is string theory, our most ambitious attempt to unify quantum mechanics and gravity. String theory requires extra dimensions beyond the three of space and one of time we experience, and the mathematics allows for an enormous number of ways these extra dimensions could be configured, something called the string theory landscape. Each configuration would give rise to a universe with different physical laws and constants. There might be 10 to the 500th power or more possible universes in this landscape, each one real, each one existing somewhere in a vast multiverse. Now here's where simulation becomes interesting. If there are infinitely many physical universes, some of them will inevitably develop intelligent life. Some of those civilizations will develop the technology to create simulated universes. Those simulations might themselves contain civilizations that create simulations, leading to simulations within simulations nested indefinitely deep. How many total universes are there? One physical base reality, let's say. Though probably many if the multiverse is real. But potentially infinite simulations, each physical universe spawning many simulations, each of which might spawn more. The mathematics becomes overwhelming quickly. Even if only a tiny fraction of civilizations create simulations, even if each creates only a few, the number of simulated realities would vastly exceed the number of base physical realities. This is the core of Nick Bostrom's argument. If simulated realities outnumber base reality by billions or trillions or infinite factors, then statistically, you're probably in a simulation. It's just the odds. But there's a deeper question here about what makes something real. If there are infinite physical universes in the multiverse, and infinite simulated universes running in those physical universes, and infinite simulated universes within those simulations, what does it mean to say that the physical ones are real, and the simulated ones are not? They all exist in some sense. Conscious beings in all of them have experiences, think thoughts, wonder about reality. What privileged status does the base physical reality have over the simulations, from the perspective of the beings experiencing them? Perhaps none. Perhaps the distinction between simulated and physical is less meaningful than we think. Both are patterns of information organized according to mathematical rules. Both give rise to conscious experiences. Both are real in the sense that matters, the sense of containing beings who exist and think and feel. The universe you're in right now, this one, might be simulated, but that doesn't make your experiences less real, your thoughts less genuine, your existence less meaningful. Or maybe there's an even stranger possibility. Maybe there's no base reality at all. Maybe it's simulations all the way down, each level running on the level below it in an infinite regress. Or maybe, as some mathematicians and physicists have proposed, all possible mathematical structures exist, and physical reality is just mathematical structure that contains observers who perceive themselves as physical. In that view, there's no difference between mathematical existence and physical existence. Both are just different ways of talking about patterns of information that have the property of being consistent and self-aware. These ideas push against the limits of what we can know or even meaningfully ask. But they show that the simulation hypothesis isn't isolated or strange. It connects to deep questions about reality that arise naturally from physics and mathematics, questions that were always there beneath the surface of existence, waiting for us to develop the concepts and the language to ask them properly. And now that we have, we find ourselves in a maze of possibilities, each as strange and beautiful as the last. There's a question at the heart of all this that we need to address directly and honestly. Can we actually know whether we're in a simulation? Is there any experiment we could perform, any observation we could make, that would definitively answer this question? Or is it fundamentally unknowable, a question that sounds meaningful but can't actually be resolved? Let's think carefully about what we can and can't know, about the limits of knowledge itself. The challenge is that sufficiently advanced simulation would be indistinguishable from base reality. If the simulators wanted to hide the fact that it's a simulation, they could. They could make the physics consistent at all scales, eliminate any glitches, respond to any test or observation in ways that maintain the illusion of objective reality. There might be no way, even in principle, to detect that you're simulated if the simulation is designed well enough and run with sufficient computational resources. This is similar to the problem of skeptical scenarios that philosophers have debated for centuries. How do you know you're not a brain in a vat, being fed sensory experiences by a mad scientist? How do you know you're not dreaming right now and will wake up to discover everything was illusion? How do you know the universe wasn't created 5 minutes ago, complete with all your memories and all evidence of history? These scenarios are logically possible, and there's no way to definitively prove them false using evidence from within your experience, because any evidence could be part of the illusion. The simulation hypothesis is the same kind of problem. Any evidence you find could be simulated evidence. Any experiment you perform could give simulated results. If you discovered something that seemed like a glitch, how would you know it was a glitch rather than just physics you don't understand yet? If you found the universe had a smallest pixel size at the Planck scale, how would you know that was a computational limit rather than just how quantum gravity works? Every piece of evidence is consistent with both simulation and base reality. Some philosophers argue this makes the question meaningless. If two hypotheses, simulation and base reality, make identical predictions for all possible observations, then they're not actually different hypotheses. They're just different ways of describing the same reality, and arguing about which is true is like arguing about whether a glass is half full or half empty. It's a linguistic choice, not a factual question. But maybe that's too quick. Maybe there are ways to test the simulation hypothesis, subtle ways we haven't thought of yet. If our universe is a simulation running on finite computational resources, there might be limits, approximations, ways the simulation cuts corners that we could detect if we looked carefully enough. The quantization of space and time at the Planck scale could be such evidence. The holographic principle, suggesting the universe has less information content than a truly three-dimensional space should, could be evidence of computational shortcuts. Or maybe we could find the source code, discover mathematical patterns in the physical laws that look like they were designed rather than emerging naturally. Some physicists have looked for such patterns, examining the relationships between fundamental constants, searching for ratios that might encode messages or signatures left by the programmers. So far, nothing conclusive has been found, but the search continues. There's also the possibility of communication from outside the simulation. If the simulators wanted us to know, they could reveal themselves, could send a message, could provide evidence that would be unmistakable, but they haven't, at least not in any way we've recognized. Maybe they will someday. Maybe they have and we didn't understand it. Maybe they can't or won't for reasons we can't imagine. Maybe there are no simulators because there's no simulation, or maybe they're bound by rules not to interfere. We're left with uncertainty, with the possibility but not the proof, with arguments and evidence that point both ways. This might be frustrating if you want definite answers. But there's another way to think about it. Maybe the question of simulation, like many deep questions about reality, is less about finding an answer and more about what the question reveals. Asking whether we're simulated forces us to think carefully about what we mean by real, about the nature of consciousness and existence, about the limits of knowledge and the strange discoveries of modern physics. The question is valuable even if unanswerable because it opens up new ways of thinking about reality, new connections between science and philosophy, new appreciation for how strange and wonderful existence is regardless of its substrate. We may never know with certainty whether we're simulated, but the journey of asking, of exploring the question carefully and honestly, teaches us things about the universe, and about ourselves that we wouldn't learn otherwise. And perhaps that journey, that process of questioning and discovery, is more valuable than any answer could be. Let that thought rest gently in your mind as we continue. Let's think carefully about what would actually change if we discovered definitively that we live in a simulation. This is worth considering because our intuition might lead us astray. You might think such a discovery would be devastating, that learning we're simulated would somehow diminish us, make our lives less meaningful or our experiences less real. But would it? Let's examine this carefully and honestly, because the answer might be more comforting than you expect. First, your subjective experience wouldn't change at all. You'd still wake up in the morning and feel the warmth of sunlight or the coolness of rain. You'd still taste coffee or tea, still feel the embrace of someone you love, still experience joy and sorrow and wonder. The qualia of consciousness, what it's like to be you, would remain exactly the same. Being simulated doesn't mean you're not having real experiences. The experiences are happening, they're being felt, they're real in the sense that matters most, the sense of being lived through moment by moment. Second, your relationships wouldn't change. The people you love would still be the people you love, whether they're made of atoms in a physical universe or patterns of information in a simulation. Love isn't diminished by being implemented differently. Connection, affection, the bonds between conscious beings, these things depend on the relationship, not the substrate. If you and I are both simulations having a conversation, the conversation is still real, the communication still meaningful, the connection still genuine. We're both conscious beings experiencing something together. That's what matters. Third, your accomplishments and growth and learning would still be yours. If you created something beautiful, it's still beautiful. If you learned something difficult, you still learned it. If you overcame a challenge, you still overcame it. The value of these things isn't that they happened in base physical reality. The value is in the experience of doing them, in the growth they caused, in the meaning they have for you and others. A simulated achievement is still an achievement. A simulated life well lived is still a life well lived. Fourth, morality wouldn't change. Right and wrong don't depend on whether we're in a simulation. Causing suffering is still bad. Helping others is still good. Kindness, compassion, justice, beauty. These values arise from conscious experience and the relationships between conscious beings. They're real whether we're simulated or not, because they're about how we treat each other, how we navigate existence together as thinking, feeling beings. The substrate doesn't change what we owe to each other, what makes life worth living, what it means to be good. Some people worry that if we're simulated, nothing matters because the simulators could turn off the simulation at any moment. But this isn't really different from our normal situation. The universe could end in countless ways. An asteroid could hit Earth tomorrow. The sun will eventually die. Heat death will claim the cosmos in trillions of years. Mortality and impermanence are already part of existence. A simulation doesn't make this worse. It just gives it a different name, a different mechanism. What matters isn't permanence. What matters is what we do with the time we have, however long or short that is. Others worry that discovering we're simulated would destroy meaning, would make everything feel hollow or pointless. But meaning isn't something the universe gives us. It's something we create through our choices and relationships and values. Meaning comes from within, from the projects we commit to, the people we love, the beauty we create and appreciate. None of that depends on the ultimate nature of reality. A simulated person finding meaning in their simulated life is experiencing genuine meaning, because meaning is an experiential, subjective thing. It's about what matters to you, not about metaphysical facts. In fact, you could argue that being simulated makes things more meaningful in some ways. If our universe was designed, if it has a purpose, if conscious beings like us are the point of the whole exercise, then our existence isn't accidental. We're not just random fluctuations in a vast indifferent cosmos. We're intentional, created deliberately, evidence of meaning beyond ourselves. The simulators, whoever they are, cared enough to create us, to let us exist and think and experience. That's not nothing. The more you think about it carefully, the more you realise that most of what we care about doesn't depend on whether we're simulated. Consciousness, relationships, beauty, meaning, morality, growth, love, all of these things are real in simulation just as they would be in base reality, because they're about the pattern, the process, the experience, not about the substrate it runs on. And once you understand that, once you really internalise it, the question of simulation becomes less frightening and more fascinating, less a threat to meaning, and more an interesting fact about the nature of existence that doesn't change what actually matters about being alive and aware in this strange and beautiful reality we find ourselves in. The simulation hypothesis raises fascinating ethical questions, both about our behaviour if we are simulated and about our responsibilities, if we might someday create simulations ourselves. These questions matter because they connect to how we should live, how we should treat each other, and what we owe to other conscious beings regardless of whether they're made of atoms or bits of information. Let's explore these implications carefully, because they illuminate what it means to act morally in a potentially simulated reality. First, if we're in a simulation, does that change our moral obligations? The answer, as we explored earlier, is almost certainly no. Morality arises from consciousness, from the capacity to suffer and flourish, from relationships between beings who can experience joy and pain. If you and I are both simulations, we can still hurt each other, help each other, love each other, betray each other. The moral dimensions of these actions don't depend on our substrate. Causing suffering is wrong, whether the suffering happens in neurons or in some computational process. Making someone happy is good, whether that happiness is felt by a biological brain or a simulated one. The experiences are real to those experiencing them, and that's what makes them morally significant. This has profound implications for how we might create simulations in the future. As our technology advances, we might reach the point where we can create realistic simulations of conscious beings. When that day comes, we'll have to think very carefully about the ethics of it. If we create conscious simulations, we're creating beings capable of suffering. We become responsible for their welfare. We can't just create them for our amusement and then delete them, or make them suffer without consequence. They would be real conscious beings deserving of moral consideration. Think about video game characters. Right now, they're not conscious. We can treat them however we want because they don't actually experience anything. But imagine a future where game characters are sophisticated enough to be conscious, to genuinely feel fear or pain or happiness. Would it still be okay to play violent games where you hurt them? Would it be ethical to create conscious beings for entertainment at all, especially entertainment that involves their suffering? These aren't easy questions, and we'll need to wrestle with them as technology advances. Some philosophers have proposed what's called the simulation argument's ethical corollary. If creating conscious simulations is ethically fraught, then perhaps most civilizations that reach that capability choose not to do it, at least not with fully conscious beings. This would be one reason why we might not be in a simulation, Bostrom's second possibility. Advanced civilizations might decide it's wrong to create conscious beings, just to study them or entertain themselves, especially if those beings might suffer. They might run simulations of unconscious physical processes, modelling galaxies and stars but not creating conscious observers. But there are counter-arguments. Creating conscious simulations might be ethical if you treat them well, if you ensure they have good lives, meaningful experiences, opportunities for growth and happiness. The creators would be like parents, responsible for beings they brought into existence, obligated to care for them but not wrong for creating them in the first place. In this view, creating consciousness is a positive good as long as it's done responsibly, adding more experience, more awareness, more beauty to the multiverse. There's also the question of whether we're obligated to try to escape the simulation or contact the creators. Some people feel that if we're simulated, we should try to hack the system, find glitches, exploit them to break free or gain knowledge of base reality. But is this ethical? The simulators, if they exist, created us and maintain our existence. Do we owe them gratitude rather than rebellion? Or are we like children who owe it to themselves to grow up and become independent? To seek truth, even if that means challenging our creators? Different ethical frameworks would answer these questions differently, and there's a deeper question about what we owe to possible simulations within our own world. If we might be simulated, and if we might someday create simulations, then there's a kind of moral symmetry. We should treat our potential simulations the way we'd want our simulators to treat us. If we want them to care about our welfare, to give us meaningful lives, to respect our consciousness, then we should do the same for any conscious beings we create. It's a kind of golden rule extended across levels of reality. Do unto your simulations as you would have your simulators do unto you. What emerges from thinking through these ethical implications is that consciousness is what matters, not substrate. Whether we're made of atoms or information, whether we're base reality or simulated, we're experiencing beings deserving of moral consideration. And if we create simulations, they deserve the same consideration from us. Ethics doesn't change based on metaphysics. It's grounded in the reality of conscious experience, in the capacity to suffer and flourish, in the bonds and obligations between thinking, feeling beings. That remains true in any reality, at any level of simulation, and recognizing that is crucial for acting morally as our technological capabilities continue to expand. We've explored the evidence, contemplated the implications, wrestled with the questions, but we've arrived back where we started in some ways, with uncertainty. We don't know if we're simulated. We probably can't know, at least not with current knowledge and technology. We're left with possibility but not proof, with arguments pointing different directions, with a question that might be unanswerable. How do we live with that uncertainty? How do we navigate existence when such a fundamental question about reality remains unresolved? Let's think about this carefully, because learning to live with uncertainty is perhaps one of the most important skills for a thoughtful person. The first step is recognizing that uncertainty is normal, even about fundamental things. We're uncertain about many deep questions. How did the universe begin? What happens after death? Is there meaning built into reality, or do we create meaning ourselves? Are we alone in the cosmos or surrounded by other minds? These questions have been asked for thousands of years without definitive answers, and that's okay. Uncertainty doesn't prevent us from living meaningful lives. It might even enhance them, keeping us humble, curious, open to new evidence and ideas. Some people find uncertainty uncomfortable, preferring to commit to a belief about reality even without proof. They choose to believe we're in base reality, or choose to believe we're simulated, based on which arguments they find more compelling, or which possibility they prefer emotionally. There's nothing wrong with this as long as they hold their beliefs lightly, remaining open to changing them if new evidence emerges. Having working assumptions about reality can be psychologically useful, giving you a framework to think within, even if you acknowledge it might be wrong. Others embrace uncertainty, suspending judgment on unanswerable questions, content to say _quote, _6_ and mean it. This approach has its own beauty, a kind of intellectual humility and honesty. You acknowledge the limits of your knowledge without pretending to certainty you don't have. You hold possibilities in mind without collapsing them into definite beliefs. This can be liberating, freeing you from the need to defend a position you can't prove, letting you explore ideas without commitment. Let's linger a moment with this idea of not knowing, of uncertainty, because there's something profound here that deserves careful attention. We live in a culture that often values certainty, that rewards confident claims and decisive answers. Admitting you don't know something can feel like weakness or failure. But there's another way to look at it, a way that finds beauty and even joy in the questions we can't yet answer, in the mysteries that remain despite our best efforts to solve them. And the simulation question, precisely because it might be unanswerable, can teach us something important about how to hold uncertainty with grace. Think about what it means to truly not know something fundamental about reality. It means you're living in a universe that still has secrets, that hasn't yet revealed all its mysteries to us. That's remarkable. That's wonderful. We've learned so much, mapped the cosmos from the Planck scale to the observable universe horizon, from the Big Bang to the present day. We understand atoms and stars and evolution and consciousness at levels of detail that would astound our ancestors. And yet, fundamental questions remain. We don't know if we're simulated. We don't know what consciousness is or how it arises. We don't know why there's something rather than nothing, why the universe exists at all, or why it has the laws it does. These mysteries aren't failures of science or philosophy. They're features of reality, maybe even permanent features. Some questions might be unanswerable not because we're not smart enough, but because they're beyond the boundaries of what can be known from inside a universe, inside a particular level of reality or simulation. We're like characters in a story trying to determine whether they're fictional. The question makes sense, has meaning, affects how we think about ourselves, but might not be resolvable using only evidence available from within the story itself. This connects to a concept in logic and mathematics called Gödel's incompleteness theorems, proven by Kurt Gödel in the early 20th century. Gödel showed that any sufficiently complex logical system contains statements that are true but unprovable within that system. You can't use mathematics to prove all mathematical truths. There are always some statements that are true but that you can't prove using only the axioms and rules of the system itself. You'd need to step outside the system, add new axioms to prove them. Perhaps reality has a similar structure. Perhaps there are truths about our universe that can't be proven from within the universe using only evidence accessible to us. Whether we're simulated might be one such truth, true or false, but unprovable from our perspective. If so, then uncertainty isn't a temporary state we'll eventually overcome with better science. It's a permanent feature of our situation, a limit on what beings like us can know about the reality we inhabit, and that's okay. That's beautiful in its own way. As we near the end of our long exploration together, let's return to what we can say with certainty, to the foundations that remain solid regardless of whether we're simulated or not. We've wandered through quantum mechanics and philosophy, through ancient wisdom and modern physics, through questions that might have no answers. But there are some things we can know, some truths that don't depend on the ultimate nature of reality, and it's worth gathering them here, holding them close, remembering what's unshakable even in a universe that might be stranger than we can imagine. You are conscious. This is the one absolute certainty, the foundation Descartes found when he doubted everything else. You're aware of reading these words, aware of your own thoughts, aware of being aware. I think. Therefore I am remains true whether you're biological or simulated, whether you're made of atoms or patterns of information. The fact of your consciousness, your subjective experience, your inner life, is undeniable. Whatever else might be illusion, that isn't. You exist as an experiencing being, and that existence is as real as anything can be. Perhaps the only thing that's ultimately real in a way that can't be doubted or diminished by any revelation about reality's underlying structure. Your experiences matter to you. Pain hurts whether it's happening in neurons or in some computational substrate. Joy feels good. Love is meaningful. Beauty moves you. These experiences have their own reality, their own validity, independent of metaphysics. If you're happy, you're having the experience of happiness, and that experience is real. If you're suffering, you're having the experience of suffering, and it's just as real, just as deserving of compassion and care. The quality of your experiences, the texture of your inner life, doesn't depend on simulation versus base reality. It just depends on what you're experiencing moment by moment, and those experiences are irreducibly, undeniably real to you. Your relationships with others are meaningful. The people you love, the connections you've built, the bonds of affection and trust and shared experience. These things have value that doesn't depend on whether the people are biological or simulated. What matters in a relationship is the connection between conscious beings, the way you affect each other, care for each other, understand each other. Substrate is irrelevant to that. Two simulated people loving each other are experiencing real love. Two simulated people trusting each other are experiencing real trust. The relationship exists in the space between consciousnesses, not in the material or computational stuff that implements those consciousnesses. Your choices matter. When you decide to be kind rather than cruel, to help rather than harm, to create rather than destroy, you're making a real choice with real consequences. Other people experience the results of your actions. You experience the person you become through your choices. This remains true in simulation just as it would in base reality. Your agency, your ability to choose and act, is a feature of your consciousness, not of your substrate. You can choose how to live, what to value, how to treat others, and those choices shape both your inner experience and the experiences of people around you. The universe is beautiful. Stars shine, galaxies spiral, quantum particles dance their strange dances, music moves us, art inspires us, the elegance of mathematics, the complexity of life, the vastness of space and time, all of these things retain their beauty regardless of whether they're fundamental or emergent, physical or simulated. Beauty is a quality of our experience, something we perceive and feel, and that perception and feeling are real. A simulated sunset is beautiful to a simulated observer, in exactly the same way a physical sunset is beautiful to a physical observer, because beauty exists in the experience, in the appreciation, in the consciousness encountering the phenomenon. Truth still matters. Even if we can't know ultimate metaphysical truth about simulation, we can still seek truth about the reality we experience, understanding how physics works, how life evolves, how societies function. Knowledge is valuable whether we're in base reality or a simulation. Understanding enriches experience, enables us to navigate our world more effectively, satisfies our curiosity, connects us to something larger than ourselves. The scientific method, careful reasoning, honest inquiry, these remain the best tools we have for understanding whatever reality we find ourselves in. Meaning is something we create. We've touched on this before, but it bears repeating. Meaning doesn't come from the universe, from being in base reality versus a simulation. It comes from us, from what we care about, what we commit to, what we value. A simulated person who dedicates their life to helping others is creating meaning just as much as a biological person doing the same thing. The dedication is real. The helping is real. The meaning generated by the choice to care and act is real. We make our lives meaningful through how we live them, and that power remains ours regardless of what reality ultimately is. These truths, these certainties, are enough to build a life on, enough to find purpose and connection and beauty and joy, and they remain true in any universe, at any level of reality, for any conscious being trying to understand their place in the strange and wonderful mystery of existence. The simulation hypothesis, even if we can't prove it true or false, offers us something valuable, a different lens through which to view reality, a new perspective that can shift how we understand existence, even if it doesn't change what we do day to day. Let's explore what insights this perspective offers, what we can learn from seriously entertaining the possibility that we might be patterns of information in a vast computational process. Because sometimes thinking about a question transforms how we see the world even if we never settle on a definitive answer. First, it encourages us to think of reality as information rather than as stuff. This shift is profound, moving from a materialist worldview where particles and fields are primary to an informational worldview where relationships and patterns are primary. When you think of yourself as information, as a particular organization of data being processed in a particular way, you start to see connections you might have missed before. You understand how consciousness could be implemented in different substrates, how the same person could theoretically be copied or backed up, how what makes you you is the pattern, not the particular atoms that currently implement that pattern. This perspective also makes certain features of quantum mechanics less mysterious. The observer effect, entanglement, the wave-particle duality. All of these become more intuitive if you think of reality as information being computed rather than as solid stuff existing independently. Of course, particles don't have definite positions until measured if position is something the simulation computes only when needed. Of course, entangled particles are connected across space if they're parts of a single information pattern that the simulation is tracking. The strangeness of quantum mechanics starts to feel less strange, more like features you'd expect in a well-designed simulation. The simulation perspective also changes how we think about consciousness. Instead of the hard problem, how does matter create mind, you have a different framing. Consciousness is what information processing feels like from the inside. Certain patterns of information, when organized in certain ways and processed according to certain rules, become aware of themselves, generate inner experience, have a subjective point of view. This doesn't solve the mystery completely, but it reframes it in a way that might be more tractable, connecting consciousness to computation, rather than treating it as something utterly separate from physical processes. And thinking about simulation connects our situation to something we already understand: computer programs and virtual realities. We've created simple simulations ourselves, video games and virtual environments. We understand how they work, how they generate persistent worlds from code and data, how they can contain entities that behave as if they have their own goals and agency, even though they're just following programmed rules. Imagining our universe as a much more sophisticated version of something we already partially understand makes it less alien, less incomprehensible. Even if the full details remain beyond us. The simulation lens also offers a different perspective on meaning and purpose. In a purely physical universe that emerged from random quantum fluctuations, we're cosmic accidents, unintended byproducts of blind forces. But in a simulation, we might be intentional, created for a reason, evidence of meaning beyond ourselves. The universe might have been designed specifically to allow for consciousness, for observers, for beings who could wonder and question and explore. Whether this is more comforting or less depends on your perspective and what you value, but it's a different framing, one that some people find more satisfying than pure materialism's account. It also encourages intellectual humility, reminding us how much we don't know about reality's fundamental nature. When you take seriously that you might be in a simulation, that everything you experience might be rendered appearance rather than fundamental reality, you become more cautious about claiming certainty. You hold your beliefs more lightly. You're more open to radical new ideas, because you've already entertained the idea that reality might be radically different from how it appears. This openness, this humility, is valuable for any intellectual pursuit, making you more likely to recognize when you're wrong and update your thinking accordingly. And perhaps most interestingly, the simulation perspective offers a kind of comfort about existence's deepest mysteries. Why is there something rather than nothing? In a simulation, the question transforms. The simulation exists because the simulators created it, and they exist in some other reality with its own existence that needs explanation. You haven't solved the mystery, but you've moved it one level up, relocated it, and sometimes that's enough. Why does the universe have these particular laws and constants? Perhaps because they were chosen to produce interesting results. Again, not a complete answer, but a framework for thinking about questions that otherwise seem utterly unapproachable. None of this proves simulation, but it shows that the perspective is valuable. That thinking through the implications of the hypothesis teaches us things about consciousness and reality, and knowledge that we might not have learned otherwise. Sometimes the journey matters more than the destination, and thinking carefully about simulation is a journey worth taking regardless of where you end up, because it opens up new ways of seeing, new questions to ask. new connections to make between ideas that seemed unrelated before. And those new perspectives enrich our understanding even if we remain uncertain about ultimate truth. Let's step back now and look at everything from the widest possible view, from what astronomers call the cosmic perspective, seeing our situation in the context of the entire universe, all of time and space, the vast sweep of existence from the Big Bang to whatever end awaits. From this vantage point, the simulation question takes on different dimensions, connecting to deeper questions about why anything exists at all, about our place in the enormity of it all, about what it means to be a small, temporary pattern of awareness in an almost incomprehensibly large cosmos. The universe is vast beyond imagining. The observable universe extends about 93 billion light-years across, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars. Most of those stars have planets. Many of those planets might harbour life. Some of that life might be intelligent. Some of those intelligences might be far older and more advanced than we are, having had millions or billions of years to develop beyond where we are now. In a cosmos this large, this old, this complex, anything that's possible has probably happened countless times. If simulations are possible, if conscious beings can create realistic simulated universes once they reach sufficient technological advancement, then in a universe with trillions of opportunities for such advancement to occur, simulations probably exist in vast numbers. The cosmic perspective makes simulation more likely just through sheer scale. With that many civilizations, that much time, that many chances for simulation technology to be developed and used, the number of simulated realities could vastly exceed the number of base physical realities, making it statistically probable that any given conscious being, including you, exists in a simulation rather than base reality. But the cosmic perspective also offers comfort through insignificance. You're a pattern of information processing that has existed for a tiny fraction of cosmic time, will exist for a tiny fraction more, occupying a tiny region of an almost infinite space. Whether you're simulated or base reality, you're temporary and small, and there's peace in that, a letting go of ego, of self-importance, of the burden of trying to be permanent or significant in cosmic terms. You're not. You're a brief moment of awareness in an eternal universe, a small eddy in vast currents, and whether you're made of atoms or data doesn't change that basic fact. Yet you're also remarkable from the cosmic perspective. You're the universe becoming aware of itself. Through your consciousness, the cosmos can contemplate its own existence, ask questions about its nature, create meaning and beauty and understanding. Carl Sagan expressed this beautifully when he said we're made of star stuff, atoms forged in the hearts of dying stars, the cosmos's way of knowing itself. This remains true whether we're simulated or not. Even in a simulation, you're a pattern of complexity and awareness that emerge from simpler beginnings, organise matter or information or whatever the substrate is into something that can think and feel and wonder. The cosmic perspective also reveals how young we are as a species. Humans have existed for perhaps 300,000 years, civilization for maybe 10,000, modern science for a few hundred years. We've just begun to understand the cosmos, just started to ask the deepest questions about reality. We're children in cosmic terms, early in our development, far from whatever we might become if we survive and continue growing. From this perspective, not knowing whether we're simulated makes sense. We wouldn't expect children to understand everything about their situation. We're still learning, still developing the concepts and tools we'll need to answer deeper questions. And if we are in a simulation, the cosmic perspective suggests that base reality is even vaster than our universe, containing not just our cosmos but the infrastructure to simulate it, plus perhaps countless other simulations, plus whatever civilization created all of this. The scale would be staggering, making our universe, already almost incomprehensibly large, just one small element in something even greater. This nested infinity, realities within realities, each one vast in its own terms but small relative to what contains it, is dizzying to contemplate but also magnificent, a vision of existence that transcends any simple account. Or perhaps there's no base reality at all, just simulations all the way down, infinite regress, each level simulating the next, no ground, no foundation. Just layers of reality extending forever. Or perhaps, as Max Tegmark proposed, all possible mathematical structures exist, and existence itself is just mathematical pattern, information organization without substrate, meaning without matter. The cosmic perspective opens up these vast conceptual spaces, these vertiginous possibilities that humble our understanding while expanding our sense of what existence might encompass. What we're left with is awe, wonder at the sheer strangeness and magnitude of existence, appreciation for the mystery that remains after all our questions and explorations. The cosmic perspective doesn't answer whether we're simulated, but it places that question in context, shows it as one thread in an enormous tapestry of mysteries, one question among countless others about this strange, beautiful, incomprehensible reality we briefly participate in before returning to whatever nothingness or transformation awaits us. And perhaps that context, that sense of scale and wonder, is more valuable than any answer could be, because it keeps us appropriately humble and appropriately amazed, two attitudes that serve us well as we navigate our small lives in this vast and mysterious cosmos. We're approaching the end of our journey together through this question of simulation and reality, and I want to spend some time here in these final chapters talking about peace, about how to carry these ideas forward without them becoming burdens, about how to hold mystery and uncertainty as gifts rather than problems. Because the simulation question, like many deep philosophical questions, is ultimately about how we relate to not knowing, how we live with questions that might never be answered, how we find meaning and contentment even when fundamental truths remain elusive and unclear. There's a human tendency to want closure, to want definite answers, to want to resolve uncertainties and move on. We feel uncomfortable with open questions, with loose ends, with possibilities that remain unsettled. This discomfort can drive us to premature conclusions, choosing to believe something, anything, just to escape the tension of not knowing. But there's another way, a way of holding questions gently, staying with uncertainty without collapsing it into false certainty. Finding peace not through answers but through acceptance of mystery itself. Think about other mysteries in your life, personal ones. You probably don't know exactly what will happen tomorrow, next year, in a decade. You don't know for certain what other people think of you, what their private experiences are like, whether they feel things the same way you do. You don't know why you exist, why you're you rather than someone else, what happens after death, what consciousness is. These uncertainties are part of being human, woven into the texture of existence, and you've learned to live with them, to act and choose and build a life despite not having definitive answers to fundamental questions. The simulation question is similar. It's profound, it's interesting, it connects to deep issues in physics and philosophy, but ultimately it's another uncertainty, another mystery to carry alongside the others. And like those other mysteries, it doesn't prevent you from living well. You can wonder about simulation while still getting up in the morning, pursuing your goals, loving the people you love, finding beauty and meaning in your days. The mystery can be background, something you think about occasionally, something that adds depth and strangeness to your understanding of existence without dominating your attention or paralyzing your action. Making peace with mystery requires a certain kind of trust, not trust that answers will come, but trust that you can live well without them. You trust that your life can be meaningful even if you never know for certain what kind of reality you inhabit. You trust that you can make good choices, build good relationships, create value and beauty. All without resolving every metaphysical question first. This trust is practical wisdom, the recognition that knowledge is always incomplete and that's okay. We can still navigate existence successfully, with the imperfect understanding we have. It also requires recognizing that some questions might be valuable precisely because they don't have answers, because they keep us wondering, keep us humble, keep us aware of how much we don't know. If we knew everything, if all mysteries were solved, we might become complacent, closed to new ideas, certain of ourselves in ways that prevent growth. Mystery keeps us open, keeps us curious, keeps us ready to be surprised by what we discover. The simulation question, by remaining unresolved, serves this function, reminding us that reality is stranger than we know, that there's always more to discover, always deeper to go. Making peace with mystery also means not letting it create anxiety or existential dread. Some people, when they first encounter the simulation hypothesis, feel unsettled, even disturbed. If nothing is certain, if reality might be fundamentally different from what it appears, how can anything matter? How can we trust our experiences? But this reaction, while understandable, is based on a mistake. It assumes that meaning and value depend on metaphysical certainty, that we need to know ultimate truth before we can live meaningful lives. But we don't. Meaning comes from within, from what we care about and commit to, not from external validation or metaphysical guarantees. You can find peace by shifting focus from questions you can't answer to questions you can, from metaphysics to ethics, from what reality ultimately is to how you should live in the reality you experience. Instead of quote 8 ask, quote 9, quote 10, quote 11. These are questions you can make progress on. Questions where your choices matter. Questions that lead to action rather than speculation. And in acting on them, in living according to your values, you create meaning that doesn't depend on knowing whether you're simulated. The peace comes from acceptance, from saying underscore quote underscore 12 underscore. This acceptance isn't giving up on understanding. It's recognizing what you can and can't know, what matters and what doesn't, what's worth your attention and what can be gently set aside. And in that recognition, in that acceptance of your situation as a limited being in a mysterious universe, you find a kind of freedom, a lightness, a peace that doesn't depend on having answers but comes from being comfortable with not having them. As we approach the very end of our long exploration together through quantum mysteries and philosophical questions, through ancient wisdom and modern physics, through uncertainties that might never be resolved, I want to leave you with something positive, something uplifting, something that transforms the simulation question from a source of anxiety or confusion into what it really is, a profound gift, an invitation to wonder, a doorway into deeper appreciation for the strangeness and beauty of existence. Because that's ultimately what this is about, not proving or disproving simulation, but opening ourselves to the remarkable mystery of being here at all. Conscious and aware in a universe that gives rise to consciousness and awareness. Wonder is a particular kind of feeling, distinct from mere curiosity or surprise. It's a sense of awe mixed with humility, an appreciation for something vast or profound or beautiful that transcends complete understanding. You feel wonder looking at stars scattered across a dark sky, contemplating that each point of light is a sun like ours, many with planets, many of those planets potentially harbouring life, all of it so far away that the light you're seeing left those stars before you were born, before your parents were born, sometimes before our species existed. You feel wonder watching a baby learn to smile, marvelling at consciousness emerging, a new person becoming aware of being aware, entering into the community of minds. The simulation question, approached rightly, produces this same wonder. Whether we're in a simulation or base reality, the mere fact that we can ask the question, can understand quantum mechanics and information theory and philosophy well enough to even formulate the hypothesis is remarkable. We're patterns of matter or information that have organized themselves into beings capable of contemplating their own existence, asking questions about their reality's fundamental nature. We've gone from amino acids in primordial oceans to creatures who can split atoms, sequence genomes, send machines to other planets, and wonder whether the entire universe might be a simulation. That's extraordinary, miraculous almost, regardless of what the answer to the simulation question turns out to be. And the strangeness revealed by physics, the quantum behaviours we've explored, the entanglement and superposition and observer effects, these things would be wonderful even if they didn't suggest simulation. They show that reality at its most fundamental level is profoundly weird, operating according to principles that defy common sense, but that we can nevertheless understand mathematically and verify experimentally. We live in a universe where particles can be in multiple states simultaneously, where they can be connected across arbitrary distances, where observation appears to affect what's observed. This is amazing, wondrous in the deepest sense, revealing a cosmos far stranger and more interesting than the solid, predictable clockwork universe our ancestors imagined. The simulation hypothesis doesn't diminish this wonder, it enhances it, adding another layer of strangeness and possibility. If we're simulated, then not only does our universe have all these remarkable quantum properties, but it's also nested inside something even larger, created by minds we can barely imagine for purposes we don't understand. The scale of existence expands, the mystery deepens, the possibilities multiply. And even if we're not simulated, the fact that we can seriously entertain the hypothesis, can recognise that we couldn't distinguish simulation from base reality if the simulation were well designed, reveals something profound about the limits and possibilities of knowledge, about consciousness and computation, about what it means for something to be real. Wonder keeps us humble, reminding us how much we don't understand, how small we are against the vastness of existence, how recent our knowledge and how tentative our understanding. But it also elevates us because we're part of this marvellous cosmos, participants in its unfolding, observers and actors both. We're not separate from the universe wondering about it from outside. We're the universe wondering about itself, matter or information or whatever we're made of, becoming aware and curious and filled with the desire to understand. That's a privileged position, a remarkable one, worthy of appreciation and gratitude regardless of metaphysical details. So as you carry these ideas forward from here, as you think occasionally about simulation and reality, quantum strangeness and philosophical puzzles, let them be sources of wonder rather than anxiety. Let them remind you how mysterious existence is, how far beyond complete understanding, how strange and beautiful and improbable that you're here at all, conscious and aware and able to contemplate these deep questions. Let them make you more curious, more humble, more appreciative of the mystery. Let them open you to possibility, to the recognition that reality might be stranger and more wonderful than you can imagine, that there's always more to discover, always deeper to go, always new perspectives that transform how you see everything. Wonder is the appropriate response to existence, the feeling that fits our situation as temporary patterns of awareness in a vast, strange, beautiful cosmos that we're only beginning to understand. And the simulation question, by revealing just how strange reality might be, by showing us possibilities we wouldn't have imagined otherwise, by teaching us about quantum mechanics and information theory and the limits of knowledge, serves wonder well, keeps it alive, nurtures it, gives it new dimensions to explore. That's the gift, not an answer, but a deepening of the question, not certainty, but richer uncertainty, not knowledge, but wiser ignorance. And these are treasures worth carrying forward as we move from these contemplative hours back into ordinary life, back into the reality we experience moment by moment, whatever its ultimate nature might be. We've travelled together for 2.5 hours now, through quantum mysteries and philosophical questions, through ancient wisdom and modern physics, through possibilities that stretch the imagination and uncertainties that might never be resolved. From the double-slit experiment to the simulation hypothesis, from consciousness to cosmic perspectives, from what we can know to what we can never know, we've explored one of the deepest questions anyone can ask. What is the nature of the reality we inhabit? And the answer, as honestly as I can give it, is that we don't know with certainty. We probably can't know, at least not now, with current understanding and technology. The evidence points in interesting directions. Quantum mechanics suggests things about reality that fit surprisingly well with simulation. Fine-tuning and mathematical structure and the Planck scale all create suggestive patterns. But nothing proves it definitively, and maybe nothing can. We're left with wonder and uncertainty, with mystery that remains mysterious despite our best efforts to solve it. But what we've learned is that this uncertainty doesn't diminish us. Whether we're in a simulation or base reality, we're conscious. We experience, we love and create and wonder. We're the universe becoming aware of itself, asking questions about its own existence. And that's remarkable regardless of what answers we discover. The substrate doesn't matter nearly as much as we might think. What matters is the pattern, the process, the experience of being alive and aware in this strange and beautiful cosmos. If you enjoyed this slow drift through deep questions, a like and subscribe really helps others find these contemplative explorations. And to those already here, those who've stayed for this entire journey, thank you deeply for trusting me with your evening, for letting me share these ideas and questions that fascinate me, for wondering alongside me about the nature of existence. I hope you found something valuable in these hours, some insight or perspective, or simply the pleasure of thinking about profound questions in a calm, unhurried way. Wherever you are in the world right now, whatever time it is where you're listening, I hope you're comfortable. I hope your breathing has slowed, become deeper and more natural. I hope your thoughts have quieted, finding a rhythm that's peaceful rather than anxious. I hope your body feels heavy and warm, ready for rest, released from the day's tensions and worries. Look up at the stars if you can, or imagine them if you can't. All those points of light scattered across the darkness, each one a sun, many with planets, all of it held together by gravity and quantum forces, all of it following mathematical laws we've only begun to understand. Whether they're simulated or base reality, they're still beautiful, still worthy of wonder, still evidence of something vast and profound that we're privileged to be part of for our brief moment of existence. Sleep well tonight. Dream of quantum possibilities if you dream at all, of universes nested within universes, of consciousness spreading through the cosmos, of mysteries that remain mysterious but beautiful because of it. Rest in the knowledge that you exist, that you're aware, that you're part of this grand, strange adventure of existence, however it's ultimately structured. Good night.